Okay, so we are at our last meeting, and we have several things we could discuss. Probably not all of them we're going to discuss. But I think talking about quantum optics without talking about Bell inequalities and understanding where they come from would be considered a crime. So maybe we'll do that, or at least start with that, and then hopefully say something about the interaction of two-level system with a quantum field, if we have time for this. So that's an open question. So we want to talk about, well, I could say this is EPR. It's not exactly EPR. Because the Epr paradox was related, or the way it was originally formulated, the Epr paradox was related to continuous variables such as position and momentum, and specifically in the Epr paradox, the state, you have two you could write a wave function of two particles. Suppose that we do it in the position, and that would be, and it is like that. Something like this. So this is what Einstein was thinking of. Two particles that are located at the same position, but you don't know where. So it's a superposition of possibilities where the two of them are at the same location, but you don't know where. If you check and transform this to the momentum basis, you can write it very similarly. This is really the same state, meaning that if you transfer to the momentum basis, this will become integral dp1 delta of p1 plus p2. So if you are in a state like this, you'll have them. So the two. What? To transfer to the momentum basis, in this case, actually, yes. It should come out P1 plus P2. By the way, they should. If I can, let's think of this in some other way. When I talk about two variables, I can talk in terms of x1 and x2, or I can talk in terms of the sum and difference. So I can move to x prime, x1 prime, or I don't know. Let's call this y1 equals x1 minus x2, and y2 equals x1 plus x2. And under these, of course, the state is yeah, well, will be so and okay. Wait, I'm not interested in the state so much. What I wanted to say is that this is related. This is this is a coordinate. I mean, you can describe the x coordinates in terms of x1 and x2, or in terms of these. This is just this is just the rearrangement of the coordinates. If you're working in x1 and x2, then you can move to working at y1 and y2. So it's just still a point in x1, x2 is described just as well. But the point is, this relates to the conjugate variable of x1 minus x2 is the variable p1 minus p2. And the conjugate of this one is p1 plus p2. Now, if this is a delta function, meaning if we know that x1 minus x2 is 0, this is what this state says. You know exactly the difference in position. Then it means that p1 minus p2, if this one goes to 0, then this one must diverge by uncertainty. Look, we're talking about, you know what, let's even write this for a moment. And on the other hand, this one we don't know. Now, if you look at what we just said, when this is the state, then if you ask me what is x1 plus x2, it could be anything. x1 and x2 are the same value, and they could be anything anywhere. So their sum is anything anywhere. So this one is diverging. Let's write it like this. This one's diverging. And this one, it can go to 0. Now, a quick reminder, if we think about a free, if we think about two free particles, so we have p1 squared over 2m plus p2 squared over 2m, maybe m1 and m2, but or, of course, I can write this as let's call this p1 plus p2 equals ps, being sum, and p1 minus p2 equals pd, meaning difference, and therefore p1 equals ps plus pd, half, but no, I'll call this one half, okay, just so that it will be convenient, and p2 equals ps minus pd, and we can put that back in there, and we'll get ps plus pd squared over 2m plus ps minus pd squared over 2m And you'll clearly see that what you'll be left with is PS squared over 2m plus PD squared over 2m. Because the intermediate term, the mixing term vanishes. So it's the same thing. I mean, this is just a different pair of coordinates, the same system. So, yeah, and we can discuss a situation where maybe this P sum is very well defined, and this PD is not, or all the other ways around. Okay, so that was how Einstein considered EPR, and specifically he was saying the main thing was this. Look, those two particles, I mean, this wave function is of course something that exists, it's a function of time. It will evolve. Now, those two particles, they have momenta. They're opposite momenta. So they're flying in opposite directions. Now, and you know, a delta function is never really a delta. And an integral from minus infinity to plus infinity is never really from minus infinity to plus infinity. This is only what mathematicians do. For physicists, minus infinity to plus infinity is from sufficiently small to sufficiently large. So we have a region where the two electrons were emitted from. We don't know where within that region. It's rather large. It's not really infinite. And they were both emitted from the same place, but I don't know where. So to describe this kind of thing, where would it come from? I don't know. I have like something like a decay. I have an unstable medium with many, many atoms in it. And at some point, one of them, I don't know which, decayed into two particles. The sum of their momenta is the total momentum, which was 0. So they have opposite momenta. And they're flying at opposite directions, apparently. And I don't know where it happened within the medium, but the medium is okay. I mean, compared to the microscopic dimensions, it's huge, but compared to my dimensions, it's sufficiently tiny. And they're flying out of this millimeter size, and one of them is going there, and the other one's going there. Now I can do measurements on both. Okay. Suppose. Okay, so it's convenient for me now to talk about time and energy, but it doesn't really. It shouldn't be really critical. I'll explain. Okay, so they're emitted from this relatively. From here, they were emitted at a considerable large distance, and I'm measuring one of them here. So I can measure, for example, its momentum. And I'll immediately know what the momentum of the other one is, because the sum of their momenta is by definition 0. Or I can decide I'll measure its position, and suppose that I can project from it where it was emitted from. Okay? So I'll do a measurement here that analyzes exactly the position here, and from this I'll be able to analyze where it was emitted from, because after all it was moving in a straight line, or there is, we're not considering right now how exactly it is done, but let's assume that it can be done. That there's some you can put an imaging setup. You can image electrons just as well as you can photons. And you're imaging it, and you see exactly where you have a click, so you know where it was emitted from in here. And you know that the other one was emitted from the same position exactly. Now, Einstein was smart, so he said, okay, if we can do this, then you know, this state is clearly a physical state. It can be generated, probably is. And then, but he was worried with the following. He said that he believed that physics is local. What does it mean? That the results of a measurement at some time cannot depend on anything outside of anything that happens outside of its light cone. So now, so for example, if somebody is performing at the same time another measurement somewhere else, if physics is local, then there should not be any way how this measurement outside of the light cone could affect it. Specifically, if two measurements are simultaneously conducted in two different locations, they cannot have any influence on one another.
Unless they had prior influence.
Okay, so let's talk about the prior influence. That's the main point. Okay, so what worried Einstein was that if you measure, so he said, okay, you know, we cannot measure both position and momentum at the same time, because those are two different measurements. I mean, if I want to measure momentum, I need to put some kind of a spectrometer in order to something that measures velocity, and it doesn't work to measure the velocity of an electron and at the same time. So it was clear that there are really experimental problems to measure those two things simultaneously, and that if you measure one, you influence the other. And this is internal. You cannot do this on a single particle. So there are some inherent limitations to any experiment you can conduct, which will prevent you from measuring the position and momentum of the same particle. And he said, okay, but that shouldn't stop me. This is a problem of the experiment. This is not a problem of the particle. The particle does have a momentum, and it does have a position. It's just the problem of your devices and how you measure it, that you cannot infer both. And therefore, I show you an experiment where you could infer both. How? There's this electron here. Okay, measure its position. And you will know the position of the other one as well. You can't measure its momentum? Fine, don't. Measure the other one. The other one's momentum. Then you'll know that one. So you know both position and momentum of both. This, of course, so then, now this is contradictory to quantum mechanics. Quantum mechanics says, if we believe quantum mechanics, that once you measure this one, the state collapsed, and that's it. You don't know. I mean, you know this x, you know that x, and there's no way you could know anything about the momentum. Not of this one and not of that one.
זה לא גם סותר את תורת היחסות הניסוי שהוא הציע?
No.
זה העברת מידע מהמהירות האור. זה קריסה של המצב.
Up.
קלאסי.
Slow down. Actually, well, it seems like quantum mechanics violates relativity. No, quantum mechanics does work well with special relativity. It's general relativity that causes the problems. So, and then Bohr said, no, you're wrong. And he published, so if you read Epl's paper, Einstein, he was a philosopher more than he was a physicist. But this was a really good one. And he talks about, there are all kinds of definitions in there about an element of reality. And what does that mean? And if we believe in local realism, okay, and then Bohr wrote a response, which was very long and completely non-readable, and culminates to the to 3 words: it's wrong. I mean, or no, I mean, quantum mechanics is right, and you cannot do this, and that's it. Now the point is, on one hand, this was like the war between giants, those two. But the problem was that it seemed like there's no experiment that can decide which one is right. Because basically what Bohr was saying was that once you measured, the state collapsed. What exactly collapsed? And what it means is that basically that Bohr says, look, no, quantum mechanics is non-local. And once you measure something, the state collapses everywhere. And this momentum measurement that you will do on the other side, it won't tell you anything because it will be useless. But it will give you a number. You'll end up with 2 numbers. And the question is, are they right or wrong? But you won't. And then the question is, can you know or not? Because what it means is that, it seems like it's completely futile to discuss this, because this one knows position. He knows position. He measured it. So he thinks that the other one was right from this location here. They both. He tells you, you came from there also. But he doesn't know that. He didn't measure position, so he has to believe you. And when he does the measurement, he measures momentum. He tells me, you know what your momentum was? This was your momentum. I know, I measured. Well, okay, I believe you because I didn't measure. I cannot. So it seems like both of them have partial information that maybe does complement each other or not. And we don't know. Now, what do we have? So this is a standard situation of correlation. For example, there's a story about this physics professor who was very absent-minded. He would forget all kinds of things, and he would get up very early when it was still dark outside, and he didn't want to turn on the lights when he was taking out the clothes. He was, because his wife was asleep, of course, he didn't want to wake her up because he was a nice physics professor. So he would take out the socks without checking. And he had white socks and black socks. To make things interesting, he would always take out one white and one black sock, but he doesn't know which. Now, and then he wears them in the dark, and he has long pants as opposed to this physics professor. So you don't know which socks he has. But if he lifted just one sleeve or one pant, how do you call it? One. No, איך אומרים שנכנס אחד.
אין לזה באמת מילה.
איך יכול להיות?
אנשים אומרים pant leg.
One pant leg?
כן.
Okay. If he lifted one, you knew immediately what he had on the other, because you know that he always wears one white and one blue, one black, but you don't know which. Now, the point here, so is this an entanglement situation? Of course not. Each sock had a color all the time. what happened was that there was a hidden variable. The hidden variable, which was known to nobody but still existed, was some coin toss that happened at the time of taking the socks out. When he took the socks out, it was as if somebody tossed a coin and decided this one will be black, this one will be white. This is called a local hidden variable. And it appeared as if, you know, those two electrons, they once lived at the same location. So they could make any agreement that they wanted. They could have tossed a coin, they could have done many things, and they could have decided, for example, okay, this is going to be my position, and this is going to be your position, this is going to be my momentum, this is going to be your momentum. They did that according to the rules, but we don't have access to this. There is no way for us to measure or to know what this hidden variable was that decided this. Sorry. תודה. זה נשמע לכם בריא. We don't know what this hidden variable was that dictated what the position and momentum will be. And that coin toss is whatever that dictates the outcomes of both experiments. And what seems to us non-deterministic and stochastic is actually perfectly deterministic and non-stochastic if you knew, if you had a camera in the sock drawer of that physics professor, and it had some IR lamp so you could see if without waking his wife and without him noticing, then you could know a priori which leg had which sock. But so the problem is yours. The electrons, they know exactly both their position and momentum. It's just you that you cannot measure. So this was what Einstein was looking for. And Bohr said cannot happen. There is no such thing. There was no clear-cut way to decide between them. So the world stopped caring. I mean, this was a big deal in 1935. And after several years, there were all kinds of big events in the world. And all kinds... Wait, that's what we're going to talk about. But very quickly, the physics world stopped caring. Why? Because there was no way to tell. So we use quantum physics the way we understand it, and we don't care anymore. Until 1964, so this is 29 years later, when Bell wrote his inequalities. He showed that there are differences, that the correlation in quantum physics is better than the best you could do with local hidden variables. Now this is a subtle statement because it doesn't appear in the Einstein experiment. The Einstein experiment could be explained by local variables as it could have been explained by the standard quantum mechanics interpretation. The point is that, I can construct all kinds of measurements. Now, we know that if I'll measure X, I'll have perfect correlation. If I'll measure P, I'll have perfect anti-correlation. But what if I measure something like X plus P? Okay. So now this, when we talk about position and momentum, it sounds like a bit crazy. It's not so clear. But look, it is possible. I mean, you can construct, we'll move to polarization of photons in a moment. And there it would make more sense, because in photons we can ask about the polarization of the photon. I can put, but if you think about this, polarizers are also something that means that you decide in which basis you measure. So this is what they were doing. They were measuring either at X basis or at P basis. But by the way, you can construct bases that are in between. Well, come on. In theory, there's no problem to make both, you know, the canonic harmonic oscillator, you can set, if you set the mass equal to 1, then X and P are in the same units.
But in reality?
But no, there's no such thing. Or no, of course you can. I mean, just as you can talk about, you know, in light we can talk about position and momentum, and those are the quadratures, and they are measured exactly in the same. They're measured exactly in the same units. Assume you can normalize. I'm trying to explain, that was what Bell understood. And it's hard to understand on the original formulation of Einstein. Because thinking about the original formulation of Einstein, it's not so clear how could you measure some superpositions of X and P. But then this is why we'll move to discuss this in terms of entanglement, in terms of polarization of photons. This is what Bell did at the time. And then let's talk about this. You know, if I can measure, I have two photons, so I'll describe the concept originally. I have two photons, and they're emitted in an unknown polarization, but always the same polarization. So they both have the same polarization, but it could be like this, or like this, or like that, or it could be both horizontal, both vertical. So that means that I have those two photons. Luckily, they're emitted in two different directions. I can do a measurement on one, I can do measurement on the other. If I put in front of both of them this kind of polarizer, I'll get the same result. Either both of them pass through it, or both of them do not. I can put two polarizers like this. I'll also get the same result. Either both of them pass or both are not. I can put one polarizer like this and one polarizer like this. And then I know for sure that I'll have opposite results. Because if this one passed, then the other one won't. But I don't know, in any case, whatever polarizer I put, I don't know what I'll measure. Okay? But I know that if the other side put exactly the same polarizer, either at the same basis, so if he is measuring at the same basis, what is the same basis? So if I'm talking about vertical, so vertical or horizontal is the same basis. But if he measures at 45 degrees, then there's completely no correlation between our results, right? Because I know the polarization of the photon, and the other one is, he puts a 45 degrees in front of that, so he has 50-50 chance of seeing or not seeing independent of what I measure. So those two results are exactly correlated, whereas those two results are completely uncorrelated. There's no correlation between them. Now the question is, what happens in between? Suppose that, you know, I put this one like that, and this one not at 45, but at 10 degrees, 20 degrees. Okay? Those two, if those two are exactly the same, they're perfectly correlated. If they're exactly at 45 degrees, they're perfectly uncorrelated. But what in between? That's what Bell asked. And in between is to mix the bases. Because think about this. If I measure at this basis, I'm exactly measuring at the what I want to say is that X and P are what we call completely unbiased bases. If you measure X, you know nothing about P, or the other way around. Now, what about polarization? What are the bases that you could have for polarization? Well, this could be one basis. This could be another basis. There's a third one, which is and all of those are mutually unbiased. They're all, by the way, in the sense that, if I measure the polarization, if I have a photon and I measure it in this basis, I'll have some results. Or I can measure in this basis. This is the basis of sum and difference. And sum and difference is exactly where you wouldn't know anything. So those are and then I say, look, if he measures in this basis, it's like measuring in position. If this guy measures at this basis, it's like measuring in momentum. Now the point is that he can turn his polarization anywhere. Doesn't have to measure here. Now, and then the question is, how much correlation will he see? Especially when those two polarizers are not exactly the same, but a small angle between them. And here, you can try to say, what is the best hidden local variable that could be? On the other hand, what does quantum mechanics tell us? And the answer is, surprisingly, quantum mechanics give us a little bit more. So this is what we want to see. So that's what Bell's inequalities tell us. And yep. Okay. So so we want to discuss so the Bear's thought experiment. And it's not really a thought experiment because it was later performed. It took, though, quite a long time until it was actually performed. It was in 1981 that Aspe did this experiment almost as it was thought by Bell. So, I mean, if you put if I have a polarizing beam splitter and I throw in a photon, it could come out here or there. It can come out here or there. Let's call this. If I have a click here, then I would say this was a single photon at basis X. So that measures the polarization. And if I saw it here, if I put a detector here and I'll measure it here, that would be the photon was on y. So let's, instead of writing, we're going to talk about single photons all the time. So we'll call the state that the photon passed x. Everything is always at a single photon. And we'll call the state that it came out here y. So we agree that this means a single photon at x polarization, and this one means a single photon at y polarization. And x and y are for us the orientation of that polarizing beam splitter. Now, and I can associate an operator. So this is one photon in x polarization. And I can talk about what is the operator for a polarization measurement. Okay? So in that basis, if I measure like this, in this basis, the operator of polarization measurement is a diagonal operator, right? Then so I can say that the state psi can be some alpha times x plus beta times y, or in other words, I can think of it as being a vector which equals this alpha and beta. And in this, and those alpha and beta, they have a meaning by being that the probability of measuring x is alpha squared, and the probability of measuring y is beta squared. Of course, alpha and beta are sum up to 1. We can think then that in this basis, I can talk about the operator of polarization. I use A just because this is what's written in my notebook, and this is A of some angle theta equals 0. You will understand in a moment where theta comes from, but we're measuring at this angle here, and then this is what the polarizer, it's 1, minus 1, 0, 0. Operating on this state. Suppose that if I know that I have exactly x, this is operating on x. This is to say that A operating on x equals 1 times x, and we decide that A operating on y equals minus 1 times 1. Okay? So this is the polarization measurement operator in this. Now the question in this experiment. Now we are measuring the polarization in the basis where the state is defined. I'm telling you, look, this is the state. But this state has a meaning independent of what the polarization measurement is going to be. Okay? So I can decide that I'm measuring along a different angle. I don't have to measure the polarization along, okay, so this has a superposition. Maybe it has a superposition of being, the photon has a superposition of being like this or like that. I don't know. But I'm not measuring it within that basis. I'm measuring at 45 degrees or at some angle theta to this. So what happens if, this is the state basis. Now it's not really the state basis. It's just where I know how to define, this is where I know to write the state. But I'm measuring with some theta. This is the polarizer Now, you know, if you put a polarizer at any angle, there's always a probability of the photon either coming out this way or that way. So now I want to calculate, given this state, what are going to be the probabilities of finding the photon at the outputs of the polarizer, depending on the angle of the polarizer. Now we know that if I put the polarizer at angle theta equals 0, it's alpha squared and beta squared. If I put it at angle 90 degrees, I only switch them. So it's beta squared and alpha squared. What? And then what happens in between? Now, it is, yeah. So in between, so we can talk about the polarizer basis. Let's call this, if you go out this, I'll call plus. This would be x. This is where this was the x and y. And those two we'll call plus and minus. Meaning that when I pass the polarizer, I have a different, I have a probability of having a plus. Now, so now I'm claiming that a plus state equals cosine theta times x plus sine theta times y, and that minus is minus sine theta times x plus cosine theta times y. It makes sense. Yeah. And let's see if I can, you know, in my notebook it says that it's easy to show. But, you know, we can, let me give you the final outcome, and that the operator A of theta that is non-zero, it looks like this. Cosine twice theta, sine twice theta, minus sine, minus, no, without a minus. This one remains the same. Sine twice theta minus cosine twice theta. Now, we can clearly see that when theta equals 0, then we have what we had before. When theta equals 90 degrees, or pi over 2, we exactly switch them, which is what we should have. When theta equals 45, so those two become 0, and those two are, so this becomes completely non-diagonal, and you can check that the eigenstates of this operator, we can diagonalize this operator, and we'll find that those are the eigenstates of that operator. So in the xy basis, the eigenstates of the polarization measurement, you know, it's always the same. You can write them as superpositions of the old basis. So this is, those are, we can, you know, let's make a quick check. Those are the eigenstates, and they have eigenvalues plus or minus 1. Let's just make a quick check. If I take this and multiply it by cosine theta, sine theta, which is the plus, we should get something, we should get the same thing with plus 1. So what will that be? Well, that will be a vector. What's going to be here? Cosine 2 theta times cosine theta plus cosine plus what? Sine 2 theta sine theta. And here we'll have sine 2 theta cosine theta minus cosine 2 theta sine theta. Now, we need to work a little bit. And then here we'll have, so we need to open this. There will be a, you remember that cosine theta is cosine squared minus sine squared.
Cosine theta.
What?
Yes.
Yeah. And sine 2 theta is twice sine theta cosine theta. So let's do this once, so just so we see how it works. So what we have here, okay, I'll say that cosine theta, cosine 2 theta equals 1 minus twice sine squared theta. And then you can remember also that cosine 2 theta equals 2 cosine squared theta minus 1. Both of them work. I don't think so. Wait. Now, okay, so what we have here, and sine twice theta equals 2 sine theta cosine theta. So out of this, what we have on the top, then we have minus 1 minus twice sine squared theta times. I'm going to take the cosine theta out. We'll have here cosine theta out, and this would be 1 minus sine squared, and here would have plus. This becomes 2 sine theta cosine theta, but the cosine theta is what we took out. So I'll have here 2 sine squared theta, and this went out, and we have just cosine. What do we have downstairs? Of course, here we take out the sine theta. And there we'll have 2 sine, so here we'll have 2 cosine squared theta. This is what will remain here. And here, the cosine 2 theta, we will take here. This would be minus 2 cosine squared theta minus 1. And the sine theta went out. This is the vector that we have. And the 2 cosine squared went out. And indeed, what we have is that when you operate this on that, you have that this equals cosine theta times sine theta. So this is indeed an eigenvector with an eigenvalue of 1. And you can make sure that the other one, based on the same argument, comes out with an eigenvalue of minus 1. Okay, so that was defining polarization operator and polarization basis. We didn't say anything about 2 photons yet. So far we were discussing just one. Then so, and then I can ask myself, and now we can, given those definitions, I can ask myself, what is the probability of having a plus sign, let's call this, what is P plus? P plus is the probability of seeing a plus on the polarizer. Well, and I have, what is that? It is this plus, take the state psi, take this, absolute value squared. This is what we're looking for, okay? The probability of seeing an outcome plus is what is the projection of the state that you have on the eigenstate that generates the state, the result plus absolute value squared.
So this is in the unbiased basis. Plus is the
I don't. I have a polarizer. I don't know that. Where are we heading? The state. I'll explain. The state psi is something that you don't know. All I know is what I measured and what I got.
Yeah, but we know that psi is a linear combination of x and y, not plus. I mean, here.
I could write it as the same way. This is just a selection of bases. I can write psi just as some other combination, alpha prime plus beta prime minus. And you know how to make the basis exchange. It's this. This is just
okay, just an example. I mean,
this is a measurement basis. That's the point. Now, so now, and P minus. Now, now, if you think about this, now you know. So, now then, suppose that I have a single photon in a linear. So now I want to say that I have a photon in some. So for example, if this was, and we know that, like, okay, so specifically, if the state psi is x, so plus and x. This is cosine squared theta. And all I'm saying here is just Malus law. Minus, and if the state is x, is sine squared theta. All I'm saying here, this is just nothing but Malus law. Says that, if you know that you have light in this polarization and you measure in this polarization, then it's cosine squared.
So the intensity is proportional to the probability?
Yeah. Exactly. Now, and out of this, it's clear. Now, and if the state was not x, meaning suppose that if I have a linear general polarization lambda, meaning I want to say that psi lambda defines the angle of the polarization, then you know that this is just cosine lambda times x plus sine lambda times y. This is what it means. So and clearly P plus in this case, which equals this, I don't know, plus on lambda absolute value squared, then this is going to be cosine squared of what? Theta minus lambda. And at the same way, P minus equals sine squared of theta minus lambda. Now this was really just an annoyance. I shouldn't have even written this because this is obvious. Well, if you move, okay, X and Y are just bad axes because everything is rotated. So measure relative to that. But we did this anyway. Why? Because this lambda, because now we want to move on to 2 photons and we want to ask, well, what if they agreed on some polarization? They agreed on this. Lambda is that hidden variable. Those 2 photons, they know their polarizations. Okay? They know their polarizations. They decided on it. And they just drew it. They tossed a coin and decided on the angle in which both of them are going to be. And then, no, well, but and now then, we can ask ourselves, okay, so I can do any measurements I want on those 2 photons, and I can try to ask, okay, so how well will the correlation be? Now, clearly, if I measure in the same basis, they'll be perfectly correlated, because they really have the same polarization. And if I'll measure in 2 uncorrelated bases, meaning at 0 and 45 degrees, then they would be completely uncorrelated. The question is what happens in between. And that's the point. The photons can make any agreement that they want, but they don't know what I'll ask them. So the question, they don't know what I'll measure. So, and that's why they can agree on lambda, but they don't know which angles I'll put in front of them, and I don't have to put the same angles. Specifically, I can put this polarizer at angle theta and this polarizer at a different angle. And then so now we think about this. I have a source in the center. It shoots 1 photon here and 1 photon there. And this one has, they have their state. And here we have this polarizing beam splitter. And so we have one of them goes there, one of them goes there. So let's call this, so this is what we call polarizer 1. And this one, we have here another polarizer, which we call polarizer 2. And this has, this one comes in here and it can come out here or there. So this would be plus of 1. This would be minus of 1. And this would be plus of 2. This would be minus coming out here. That would be minus of 2. State 2. And I'm asking myself, of course I can change the phase, the angle theta 1 and the angle theta 2. And I'm asking myself, what are the probabilities of having all kinds of joint measurements? Meaning, what's the probability that I'll get a plus result in both of them, depending on the various angles that I put there? Maybe I still need this definition, but too late, yeah. I always talk too much. Okay, so let's look. Now we know how to calculate everything. So for example, I can ask myself, what's the probability? And now, but let's define what's the probability of both of them having plus. What's the probability of twice getting plus? Well, the answer is, that has to do, I need to have a plus on 1 and a plus on 2. And this I should multiply with my psi, which is has an absolute value square. So this is what this means. And in the same way, I can define all of them. So there's p plus minus, of course, and this one is this plus of 1 and minus of 2. Now notice, those two states are not orthogonal. They're even not, they're not, they don't even, you cannot multiply them one with another. Because they are they could have different angles of different polarizers, and they are operating on different photons in different locations. They are not, you cannot ask yourself what is the, you know, the scalar product of those two. 0. But, and the same will go for p minus plus and p minus minus equals, they have the same definition. Now let's assume a state. So now let's write the Epr state. The Epr state, in this case, would be what? It would be 1 over square root of 2 x in photon 1 and x in photon 2 plus y in photon 1, y in photon 2. So this is a valid state. I mean, quantum mechanically, it is okay. It is, you know. What? Remember, this is the state. The state I can define in any basis I want. I define it in, say, in state x and y. By the way, you can calculate what happens if you you can do what we know could be done, which was just removed. I'm not saying. Wait, I think you're missing something. Now, remember, this is the state. I want to remind you that there's any state lambda can be written as cosine lambda times x plus sine lambda is 1. Now, you can ask yourself, okay, this is just a change of basis. And the point is that you can check. This state remains the same, even if I take a different angle. So this one's independent of the choice of basis. What?
Not according to what you wrote up top. If you change your
now wait, okay. You'll see in a moment. You know what? Let's even do this for now. So I'll take this. I'll call this. Let's call this state this. Okay, 45 degrees. This one is of course 1 over square root of 2 x plus y. Now, let me ask you, what is this? This in 1 times this, the same thing. This in 2, plus this in 1 times this in 2. I'm saying that this is a claim. This equals x in 1, x in 2, plus y in 1, y in 2. What I'm saying is that it doesn't matter. You can transform the basis of the state. It would remain an Epr state in any basis you choose. You can quickly check this. I mean, this is what happens here. This is going to be 1 over square root of 2 twice. So we'll have half outside. And then what?
Here, there's my problem. You assume that it's also 45 degrees in spaces too. How can you assume that?
No, I'm just writing this. I didn't say anything about the measurement yet. I'm just defining the state.
I think I'm comfortable, but still.
I'm defining the state. This is, I can define any state I want.
Yeah, but,
okay?
But
I have
to try to draw it.
Now listen. Listen. You have 2 photons emitted. One is going this way, the other one is going down. They have a common quantum state, just like any 2 particles. You know, 2 particles can have a joint quantum state, and it is described in the basis. Suppose that those 2 particles, they are in a 2-level systems. So, okay, this spin can be up or down. This spin can be up or down. What's the basis of both of them? Well, either both. So there are 4 options, right? Both of them up, both of them down, one up, one down, the other one like this. And the total state of the 2 electrons could be any superposition of those 4 possibilities. So now I'm taking a superposition of 2 out of those 4 possibilities. Okay? I'm telling you this is a superposition of both of them being up or both of them being down. You never have those. They don't exist. But it's a complete superposition of both up and both down. Now this is just the state. I didn't tell you what I'm going to measure. Now, what I'm showing you now, that this is independent, this state is entangled, we call this an entangled state, in any basis you would like to write it. This is still a question of the state. It has nothing to do with the measurement yet. I didn't tell you what I'm going to measure. But you can check that this is x plus y times x plus y, and this is in 1, 1, 2, 2. And this one here, there's a plus. And then what? This is x minus y, of course. So here we'll have x minus y for 1, and times x minus y. I'm tired of writing those bras and kets. For 2. And you can check. Everything here are ket times ket. So what will you get here? You'll get x, x, and from here you'll get x, x. And here you'll get plus y, y, and from here you'll get plus y, y, exactly as you need. And what about all the cross terms? They die out. They fall out because of the minus. So this, so independent of the state, independent of the basis, this state is always like this. This means that it doesn't matter. It's not that they are only correlated if you look at x and y. They'll be correlated in polarization no matter how you look. At any angle that I'll put in front of them, those 2 come out at the same polarization. I ask them in the basis of x, it's clear, they are correlated. If one is x, the other one is x also. But the point is that they are correlated no matter what I'll ask them. If I ask the same question, that's what's written here. If you ask the same question, both of them, you'll get the same answer from both of them. It doesn't matter which angle you put your polarizer in front of them. Same polarizer, same answer. Okay. What do you want me to make?
No,
you want me
it's
to
fine.
make those? You want,
It's
yeah.
fine.
Well, you're right. What?
We are.
But they are this. You know, this photon number 1 went to polarizer number 1, so they're both counted 1.
Those are two same.
And photon number 2 went to polarizer number 2.
זה עוד מתמטיקאים צוחקים עלינו לפעמים, כי אנחנו לא טובים באינדקסים.
We're terrible with indexes. Yes, they should call this photon number A, and it went to polarizer number 1, right? And A and 1 are not the same because. No. Okay, so now let's analyze okay. Now I want to say that this is my state, and all we saw, this is a state of equal probability of finding that they're both in the same polarization. I don't care which polarization I ask. And now we can ask, okay, so what is Now, here, now we should be careful because now there's angles, okay? You know, we put there that, we wrote P++, but now we should be careful. Let's write angles alpha and beta. Now, alpha and beta, or, you know what we had? Theta and phi. Meaning that those two polarizers, they're sitting at two different. Now, this one, what is that? This is what we wrote over there. This would be plus of 1. Let's call this plus of theta. And of course, but it relates to the first one. And this one would be plus of phi, it's 2. And this one, and now you take this and you cross it with that. And there's another, but let's remember another definition. What is the probability of just having plus on one of them? And I don't care about the other.
P plus 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 P plus minus.
Exactly. So this is just to say if I trace over or I sum over the other one, I don't care what the other result was. So this equals P plus plus of theta and phi plus P plus minus of theta and phi. And okay. And now we can calculate so now suppose, so I take, now we can calculate all of those. So you see, I can have all these 4 joint probabilities that exist, and out of them I can calculate any probability that I want. So I need to know these 4 numbers, but I can easily calculate them. That's not hard. So for example, I know this is my psi. And now I want you to convince yourself that given this psi, the Epr psi, so then under this P plus plus, for psi of Epr, which was 1 over square root of 2 x plus y. For this one, we will get P plus plus it depends on two angles, theta and phi. It will be then just half cosine squared theta minus phi. And P. Now, take a look. This plus on psi, I can calculate. It digs out only photon 1. And this plus in 2 on psi, I can calculate. Yeah. And make sure, I mean, you can do this calculation and figure out this is what you get. This also equals P minus minus. And the probability P plus minus of theta and phi, meaning probability that they come out, is this, half sine squared of theta minus phi. That equals to P minus plus. Now this is a quantum calculation, and it's very quick. I mean, using this definition, what do we need to do? We need to put in plus of theta. I'll use basically this. So just to clarify, let's just see one of them. We will have okay. So we want to have where did I just erase lambda? No, it's over there. So this let's calculate this guy, which is written up there. So what we will have is this. In mode 1, we will have cosine lambda x plus sine lambda y, not lambda, sorry, those were theta. So plus sine theta y, and in 2, I would have cosine phi x plus sine phi y, and all of this is in, sorry, let's put this here 1, and this one's 2. And this thing is multiplied by what we have here, and that is this x, x, and y. I'm out of board, so I'll write it here. And now we agree on the following. In whatever product we get, we multiply the first x with the first x and the second one with the second. So because there's going to be too many of them. But so you can see what will happen here. We'll have here cosine squared theta times x and x. And sine squared theta times y and y. And the others I don't care because they don't have a pair on the other side. Right? Because the other terms of this, they don't matter.
Square.
What?
Not square. So instead the cosine split, then square on everything.
No, but the point is that in the product, the product they don't agree. That they die in the product. So what we'll get here is this then cosine squared theta xx with xx. Sorry, only cosine theta right now, not yet squared. So this product is cosine theta times 1 plus sine theta times the other. And what do we get? No.
No, sure.
There should be somewhere a minus. Maybe. I need to get cosine squared theta minus sine squared theta. I don't remember.
לא, איך חסר, תקבל קוסינוס
okay.
קוסינוס תטא, קוסינוס פי.
You're right.
עוד נוסחה טריגונומטריה, קסם טריגונומטריה.
כן. Good. I'm glad you're here.
אני מרגיש צינגלות בקולך.
No, it wasn't technical. Cosine theta, cosine phi, plus sine theta, sine phi, and we'll get this, right? Yeah, everything comes. So equals cosine theta, cosine phi, plus sine theta, sine phi, which equals cosine of theta minus phi. It does. It is indeed this, and then therefore this happens. Everything else is. Now we're very happy. So this thing works. Now, so we know what will happen. We just did the quantum calculation, and we found out what is this probability of both of them showing the same output, depending on the angles of the polarizers that I put in front of them. Indeed, if I put those two polarizers at the same angle, then this probability is just half. Okay? But that doesn't tell me much. But let's see what happens. What's the probability if I don't put the same polarization in front of both of them? And we get that this goes like cosine squared. So if I ask what is p plus plus, depending on this angle delta, so on theta minus phi, so on the difference, as a function of indeed this theta minus phi, then it is this. And this is when both of them are the same, and this is when theta minus phi, it falls down to 0 when theta minus phi is at 45 degrees. So when this is pi over 4. Is this true? What's the problem? Which factor? What? No. It's half. No. Wait. The probability is half. Good. Very good. Very good.
Hey.
Now, and another thing, so let's see if this is at pi over 4 or at pi over 2. Cosine squared, apparently it should be at pi over 2. Sure. No, I'm sorry. This is, of course, at pi over 2. Something else will come up at pi over 4. But this one is p plus plus, and this one is what we would call p. This would be p plus minus. Sorry, so. And indeed, when the two polarizers, what it tells us is everything that we know. When the two polarizers are sitting the same, we have the probability half of detecting both there or not. And when the two polarizers are at 90 degrees, then it's everything now makes sense. Now let me define. And you can make sure, another thing that is important, if you remember what is p plus of theta. That was p plus minus plus p plus minus. What is that? This is half cosine squared theta minus phi plus half sine squared theta minus phi, which is half. So if you ask what's the probability of detecting a plus, no matter at which angle you put your first polarizer, you don't care about what came out in the other side, that's half. It's always half. That's okay. I don't know the polarization of the photon coming to me. I don't know. And I put a polarizer in front of it. What's the probability of measuring a plus? Half. Now, the other questions, those P++ and P+-, they are asking, oh, I want to know what happened in both cases. This one came out plus, and this one came out plus at the same time. That must be less than half. Okay? If they both were at the same polarization, it's the same. It's exactly half, because they're always at the same polarization. But if they don't measure at the same polarization, then it would be less than that. And indeed, this is what we see. So you're right, this is half here. And so finally, now let's define the function that Bell defined. Okay. So I want to define a function. Okay? So we'll call it E of theta and phi. I'll explain why E. This has to do with some expectation value. But I'll explain which expectation value it is in a moment. But this is, for now, defined P plus plus of theta and phi plus P minus minus of theta and phi minus P plus minus of theta and phi minus P minus plus of theta and phi.
Should be 1 minus?
What?
X minus minus or 1?
No. This is just because I'm writing it in two lines. So it's 1 minus. It's not.
Okay.
Yeah. Or if you want. Now, why do I call it an expectation value? You know what, before we call it an expectation value, let's calculate this. But we know what it is. P plus plus and P minus 1 minus, we know what it is. So this together is cosine squared of theta minus phi. And these together is sine squared of theta minus phi. So the whole thing is cosine squared theta minus phi minus sine squared theta minus phi, which equals cosine twice theta minus phi. So this is what this E theta and phi is. By the finish. Now, why do we call it some kind of expectation value? Because, well, let's suppose that I want to calculate we just said that if the outcome here is plus, we call this, it has an eigenvalue of +1, right? And if it comes out minus, it gets an eigenvalue of -1. So for example, if I talk about a single photon, then the average value, I can ask myself, I have this operator of the photon, or the operator of the polarization, and I can ask myself, what's the average value of that? And I can say, look, this is the state of the photons times A and the state of the photon, and we can calculate this. And this will basically be P plus of theta minus P minus of theta. Why? Because this one comes out, whatever goes for the plus has an eigenvalue of 1, and whatever comes out on the minus has a -1. And this A is just diagonal, so it does nothing except for invert the sign for this guy. So if you just had, if you ask yourself what is psi psi, this is P plus P minus, which is 1. But if you put in A inside, then you'll get this minus sign here. Now I can ask, so what about the average of A times B?
So
Or
A is measurement only in one particle, one photon?
Yeah, well, I
And B
just,
is on the another one?
yes. So I'm asking myself, what is the average of the multiplication of the polarization results? So if both of them came out plus, we say it's 1. If both of them came out minus, it's also 1, because -1 times -1 is 1. If one of them came out plus and the other one came minus, this is the case of -1, and if the other way around. So this is what's written here. We take them with plus if they have the same polarization, which means that the multiplication of their polarization is 1. So this is indeed this E of theta and phi, this A and B average is what you would call E of theta and phi. This is what E of theta and phi is. It's an expectation value of a multiplication of results. Or I could write it as being so I have here A of theta times B of phi average. This is what we write here. Now I can do this if I want, minus A of theta B of phi. Why I can do this? This is 0. I'm talking about, I'm thinking about what we have here. I want to say that this expectation, which equals this, is also the correlation. It's not just a measurement of the expectation value. It's also a measurement of the correlation between the two polarizers. Why? Because the average value is 0 of each one of them, right? A of theta, the state has an equal probability of being here and there. So the average polarization value is 0. And I can, if I want, I can divide also just to normalize this by A squared times B squared, because those are 1. This is just, forget it. I mean, those are what I did was I put here 1 at here, and this is 0. So this is, I added those things which are nothing. And then, so we got a completely valid so we got a completely, we got, now the point is this. We can measure those probabilities, right? All of them that we can measure. I mean, I'll put 2 polarizers and I'll see what's the probability of both of them coming together plus. What's the probability of both of them coming minus? What's the probability of 1 plus 1 minus? I can do those measurements. I can put 2 polarizers at any angles I want, and I can measure those 4 joint probabilities. And I can make this, out of those 4 measured probabilities, I can make this expectation value of the polarization and ask myself what it should be, and we just found that quantum mechanics tells us that this is what it should be. So it means we expect this E of theta and phi, we expect it to look like this. It looks like a true cosine. It's a cosine function, and this is indeed pi over 4 now, not pi over 2. This is the pi over 4 we were looking for. And it tells us what we knew from the beginning. And when theta equals phi, they are both looking at the same direction, then it's always 1. Why? Because those two, they never happen. When you are at pi over 2, then it's minus 1, because only those happen. Those would never happen, because the 2 polarizers are at 90 degrees to each other. And in between, it falls to 0. Now let me tell you what is the best you can do with hidden variables. And this is the point. I want to explain why the best you could do with hidden variables. This is a beautiful result. It's a quantum mechanical calculation. It wasn't hard. It just took a long time because I'm too slow on the board. But this is the best you could do classically. That's the best hidden variable you could think of. So you see, there's a violation, and the violation is largest here at pi over 8. This is where the violation is largest, because the best you could do with local variables is half, and what you get is this. Yeah. So the best you could do is half here, and this you can calculate is 1 over square root of 2. So there's a square root of 2 factor between them. Now, I need to prove that this is the best you could do. Now, with a hidden variable. Now, the point is this. When we say that there's a hidden variable, let's see, what happens, what about this state that we had there? Where is it? Our state. Here, state of the EPR. Look, this state says that each photon doesn't have a polarization. You cannot write polarization for one photon. There's only correlation between the polarizations, but each photon really doesn't have a polarization. What will we need to do in order to construct some form of a hidden variable? For to have a hidden variable would mean that the polarization exists, we just don't know it. Okay? So, and this is something that we can think of. Okay, so I can ask myself, what does it mean? So that means that those two photons, they know that their polarizations are like this. Okay? So now let's see what happens. But we put, they don't know what I will put in front of them, right? So suppose now this photon is like this. It comes to my polarizer and he sees, exactly. This polarizer stands at exactly my angle, perfect, I go through it, that's it. Now the other photon comes out according to the agreement at the same polarization. No one knows it, only the photon knows. But it sees a different polarizer. What polarizer does it see? It sees a polarizer at an angle, at 22 degrees. Now the question is, what will be and then we ask, what's the correlation between those two measurements? And then, okay, you'll see. So let's calculate exactly this.
כשלעצמו כאילו, זה סוג של דרך שבו הוא נע במרחב, לא סטרינרי או זה מעגלי או אליפסי.
But it's not. But with this state, the polarization is not defined. I'm not saying that, of course you can measure a polarization. The question is it defined? Will you get the same answer if you do this measurement over and over on the same state? And the answer for this state is no. I mean, if I give you a linearly polarized photon, then yes, every time you measure it, you'll get only this output. I want to prove that this line that I drew here is the best you could do with local variables. So we need to say something about local variables and how they could or could not work. So we assume, so now we want to Bell inequality proof. I want to prove Bell's inequality. And Bell's inequality, by the way, does not say anything about quantum mechanics. It says something about possibilities of hidden variables. So Bell says, okay, let me show you that what are we measuring here? We're measuring some kind of a correlation between results. That there's a limit on the correlation between results that could be classically, not classically, sorry, with a hidden variable. And that, and then we see that quantum mechanics violate this inequality. So we assume that there is a hidden variable. There's some hidden variable lambda, which has, I don't know what it is, by the way. It has some probability lambda. It could be some parameter. It probably that's the probability density of having lambda, and it of course makes this d lambda equals 1. So over the set of possible ranges of lambda, maybe it's an angle, maybe it's but the sum of probabilities is 1. And this is what, so when the photons meet a polarizer, they can make a decision of what the outcome will be based on this parameter lambda that they know and on the polarizer that they see in front of them. But it cannot depend on what the other photon sees at the same time. Okay? So if it's a hidden variable, then this means that the result of any measurement, so the measurement outcomes are defined by two functions. Let's call them A of lambda and theta, and B of lambda and phi. Meaning that this one and these functions, they can be either plus or minus 1. Okay? So this can either be plus or minus 1, and the question whether this will be plus 1 or minus 1 depends on the parameter lambda that the photon knows and on the polarizer that it sees. But it cannot depend on what the other photon saw. Okay, so those two functions, which are the outcomes of the those are really the polarization outcomes of the two measurements. Now, so this is what it means. And if I ask myself, for example, what is A average? What is the average result of A? That, of course, would be that would be the average result of A. That would be the integral of P of lambda A. So that would be A, the average of A of theta. Okay. Does this make sense? And let's assume, and of course, so this is, so that would be, if I measure, I'll see sometimes, maybe lambda dictates that it always comes out unity, but and let's assume that there is no polarization. We are at a situation where there is no polarization preference, right? Our output, the average polarization that we measure for any one photon is 0, because we have equal probability to measure this or that. Okay? So, in our case, A average, it doesn't matter what theta is, of any theta, equals 0. And equals also B average of phi. Because there's no polarization preference. Or in other words, P of plus equals P of minus equals half. So this is what we get. Now, as we said, there was this, what we defined as E of theta and phi. What is this going to be? This is, as we said, this is the average A of theta times B of phi. This is what we measure. So this is the average of the multiplication. This was the correlation, as we said before. And this, according to this definition, is the integral of P of lambda. What? A of lambda theta, B of lambda phi, D lambda. That's what it is. So if there is a hidden variable, there is any hidden variable, I don't know what it is, and there is some probability, if this was a probability result, somebody drew P of lambda, drew lambda out of this probability distribution P of lambda, and according to that, and the two polarizers decided on the result, then this is what this has to be. Now, let me define, so now I want to define a new variable Now remember, oh, there is something that we do want to remember. We said that A of lambda and theta is either plus or minus 1 with some probability to it. So the average of A, absolute value squared, is limited by 1, right? So what we want to say out of this has a consequence. A of theta average equals less or equal 1. This is something to remember. What? Yeah, but this is the average value of the polarization. This is not the probability.
But it defines similarly to probability.
Of course, it's related to the question of probabilities. But you have the average value of the polarization. Well, it only has two outcomes. It has plus or minus 1. And there's a probability to get each one. So the absolute value of the average result is less than 1. There's nothing very smart in it, but it is something to remember, because let us now make, we had fun with two polarizers and two angles. And if things were not complicated enough, let us now make something with 4 angles and, in a sense, like 4 polarizers. So let me define. I'm going to define a quantity that we will call S. It will depend on this lambda and on theta and phi, and on some two new other thetas, theta prime and phi prime. That's the definition. What is it? We'll call it, it has to do with these guys, with the multiplications of something like this. So this will be defined as A of lambda and theta times B of lambda and phi. Plus, minus A of lambda and theta times B of lambda and phi prime, plus A of lambda and theta prime times B of lambda and phi, plus, not A of lambda and theta prime, B of lambda and phi. Or
מינוס רק בשני.
רק בשני. Or I can define it as follows. This equals A of lambda and theta times B of lambda and phi minus B of lambda and phi prime plus A of lambda and theta prime times the same thing plus.
I never understand why one of them is with minus and the other is.
You'll see in a second. I want to say the following. This function can be either plus or minus 2. Okay? Why? Well, each one of those can be either plus or minus 1. Okay? Now, but the point is that let's think about this function b. If both of them are 1, okay? If both of them are 1 or minus 1, then this one contributes 1 and this one contributes 0. Okay? And then, I don't know what this one will be, but all it will do, it also can be plus or minus 1. So if this one is the 2, then this one can make it either plus 2 or minus 2. So the result is plus or minus 2, no matter what. There's no other possibility. Because one of those two branches is 0. Okay? If those two b's, we just said they are either plus or minus 1. We don't know what. But if both of them are plus 1, then this one, or if both of them have the same sign, then this one contributes and this one dies. And if they have opposite sign, then this one contributes and this one dies. So this S, it has only two possible values, plus or minus 2. That's all it can be. And therefore, if I ask what is S average, what's the average of S, it has to be less than 2, right? Because this is, I'll give you lambda. Now what is the average S? This is integral of p of lambda times S d lambda. But this, by definition, is going to be, and this we know that it must be less than 2, or absolute value squared. Okay? So this is the definition. But what is S average? S average is what? Is this average of this, of A of lambda, so this is the average of A let's call it the average of AB with theta and phi minus the average of AB with theta and phi prime plus the average of AB with theta prime and phi plus the average of AB with theta prime and phi prime. That's what it is. So in those averages, what? Now, then this is, oh yeah, right, sorry, right. And what we just heard is that this, and what are those? Those are the expectation values. We just wrote it before. Here it is. No, where was it? Here. That's the expectation value of those two multiplications. This is what it is. So all of those, they're expectation values of the polarization measurements. So what's written here are those guys. So it's this. This is what we have here. So saying that S is less than 1 is like saying, look, no matter what angles theta and phi you choose, whatever you want, no matter what angles you choose for theta and phi prime, the best you can have for E of theta and phi minus E of theta and phi prime plus E of theta prime phi prime, phi plus E theta prime phi prime, this absolute value squared cannot be more than 2. But now, let's put the angles that we know. So let's choose. And let's take the result that we have. So I'm going to make we know this is cosine twice cosine, we calculate this guy. Where is it? I just כרגע מחקתי אותו. So this is the Bell inequality. This is the Bell inequality, and this should get a very big, give it twice.
Very important.
This is a VIR, very important result. And then what was? But we calculated it. We know that quantum mechanically, what is that? That's E quantum mechanically of theta and phi. So, E quantum mechanically of theta and phi, this we know. This is the twice cosine of what? No, it wasn't twice. It was half. It was cosine twice theta minus phi, right? Where is it? You're right. Yeah. So that's what it was. Okay? No, there wasn't. No square. So it doesn't matter what the angles are. So look, I can choose theta and phi as I want. So I'm going to choose such that all those are 1 over square root of 2. Now 3 times 1 over square root of 2 is still not bigger than 1, than 2. But 4 times, okay, we're going to choose such that each one of those is 1 over square root of 2. Okay? We're going to choose the angles theta and phi such each one of those is 1 over square root of 2. And 4 times 1 over square root of 2 is like, so 4 times divided by square root of 2 is like 2 times square root of 2. And that is 2.828. So for theta minus phi equals pi over 8, we can get S quantum mechanically quantum mechanical equals 4 times 1 over square root of 2, which is 2.828, which is larger than 2. So quantum mechanical correlations violate the best you could think of from a hidden variable theory. Now let me explain. Let's do this a little bit more carefully. I'm going to choose what did I choose? I can choose for I'll choose for this one. You know, the problem is you can look here. So all those that I need to be positive, I'll choose for them pi over 8. So theta minus phi is pi over 8. And theta prime minus phi is pi over 8. And theta prime minus phi prime is pi over 8. But theta minus phi prime is going to be 3 pi over 8. Can I do it? Of course I can. You can check that I can choose. So I'm choosing theta minus phi equals theta prime minus phi prime equals theta prime minus phi prime equals pi over 8, and theta minus phi prime equals 3 pi over 8. Can this work? I think so. Let's choose theta to be 0. If theta is 0, then phi and phi prime. Yeah. Of course. So yeah. Well, honestly, what am I doing? There are 4, I just wrote 4 equations, linear equations, for 4 variables, theta, theta prime, phi, and phi prime. And with 4 linear equations, there must be a solution for this. So there exist those angles, they exist, and you can find them. But there isn't. You're being a mathematician now. Okay, so if we choose this, so that means that when you look at this simple case of polarizations of single photons, you can take this Epr state, you can make a prediction, and you can find that the correlation between the measurements that you have is better than the best possible classical case. So basically the prediction is, look, it should not be more than 4 times half. What comes out here? And what we get is 4 times 1 over square root of 2. And this is where quantum mechanics wins. So indeed, the quantum mechanics predicts that correlations would be better between 2 measurements are better than the best possible situation if there was a local variable. Now look, all of this depended on the fact that this function A doesn't depend on phi. So that this, that photon 1 cannot know what B is going to be. He doesn't know what phi is, and he cannot make considerations based on what the other polarizer is. So this is a local hidden variable theory. There is some hidden variable that allows you to make local decisions. And it turns out that that this predicts a limit, an upper limit on the correlation, which quantum mechanics violates. And this is because in quantum mechanics, yes, when the measurement applies to the entire state, so that means that quantum mechanics is non-local. It's a non-local theory. Now there's always this hard question: how can the photon know if the other one was measured? Now, if I made a measurement there, how can this photon know? Answer is, I don't know. But is there a transfer of information here? Meaning, it seems as if information is passing between the photons faster than light. Now, if I could ask the photon, then maybe it would answer. But now, here comes the point. Can I know? What do I mean? Okay. Miraculously, there was this wave function collapse across the universe. Everywhere around the universe, it happened in the moment somebody measured. Now, the question is, okay, if you are there measuring the photon, now I'm here, can I deduce from my measurements that you measured already? That's the point. I don't know if the photons exchange information. That cannot, I don't know about this. I cannot tell about the photons. But can the measurers exchange information? Meaning, is there anything that I can measure that will tell me if you measured already or not? Is there going to be a change? That would be an exchange of information between us, right? So you measure your photon, I measure mine. And I'm looking at my results, and without talking to you, then, aha, he already measured. If this could happen, then this would be an exchange of information. And this would be an exchange of information faster than light. But this does not happen. There's nothing. In order to know, in order to check this violation, we have to talk. We have to compare. Really, we need to, what is written here, we need to calculate the average. So we need to talk about, okay, I made 1,000 measurements, and the first one was positive, and then the second one was negative, and so on. And together we will calculate this expectation value of those angles that we choose, and we calculate this, and we find out that we violate quantum mechanics. So we violate the Bell inequality. But we have to discuss this. I mean, we do the measurements, and then we pick up the phone and talk to each other, and this is no special relativity. Okay, I mean, once we do that, there is no. Now the question is, can we not do the phone talk? Can we just, based on the measurements that we do, deduce that the other side already measured or not? The answer to this is no. If I ask because that only depends on the marginal probabilities. I'm looking at the probability outcomes that I get, and this depends only on what I do. And I ask myself, is there going to be any difference in my results if you measured already or not? The answer is no. Because for me, I'll always get half and half. So the original situation is, doesn't matter how I orient my polarizer, the probability of detecting the photon is half. Now if you make the measurement first, that doesn't change. My probability to measure any result remains half. So we don't exchange any information, and therefore we don't exchange any information faster than light. So that's it about Bell's inequalities. And that's the end of our course. I think now there are generalizations of these in all kinds of inequalities that quantum mechanics violates. And could you construct, and then the question is, what would happen if you had more than just two outcomes? What if the dimension of the system would be more? If you had the two, not just the two-level system, as we had here, two polarization outcomes, but a more complicated situation, a quantum system with more than, what we discussed is the correlation between two-level systems. You could do these kinds of calculations there as well. Actually, the inequality becomes more severe. The violation, the quantum mechanical violations become larger. And the violation when you increase the number of photons or the number of particles, then it also becomes more severe. So quantum mechanics violates those classical limits more and more as you go to higher dimension of system, more than two levels. If you go to the EPR case, you can make basically an infinite violation. But, if you have more particles, also the same. But now we stop. So I thank you all for listening to me for so long. And I hope you enjoyed the course. And we didn't discuss the two-level system with a single quantum mode, but don't worry, you will learn this. And it is, it's beautiful and interesting, and okay, I won't say anything about it now because we have to end. It's already there. No, I'm just. Okay. So, yeah, thank you. Bye. No one knows. Most likely not. What's happening there?